Okay, you should have already made your function foldable, your little note, your little book that you created in the first video. Now this is all the information you're going to put in this. So this is the notes for the function foldable, or the function book. Okay. As I already told you in that first video, we have basically four functions that we're going to talk about. We're going to talk about the linear function. We're going to talk about a quadratic function. We're going to talk about an absolute value function. And we're going to talk about an exponential function. So let's go ahead and get started. We're going to start with linear. So underneath the linear page in your book, basically you're going to write this. Linear parent function, a linear function creates a graph that is a line. Creates a graph make this a little more neat for you. Creates a graph that is a line and is a straight line. Okay, lines can go in any direction. Except vertical. And the reason that is, and we'll talk more about this in just a minute, is vertical lines are not functions. Horizontal lines, however, are functions. So keep that in mind. Okay? So far for our linear function, you have it creates a graph that is a straight line. Lines go in any direction except vertical, and vertical lines are not functions. Okay? You also need to know this, and this is very important. Linear parent function is y equals x. In y equals x, this creates a this creates a straight line, and this is the parent function. Okay, it creates a straight line like it says earlier, but it has a slope equal to 1, where we write this in algebra as m equals 1. We'll talk more about that later. Okay, and it also has a y-intercept equal to 0, or we write this as b equals 0. And again, we'll talk more about that later. So this graph, it goes from left to right. Okay, so from left to right, it goes upward, so it looks kind of like that. And the graph goes to the origin. The y-intercept means that it goes to the origin. The y-intercept of 0 means it goes through the origin. And again, for those of you who don't know what the origin is 0, 0 on your Cartesian plane. When we do a lot of scatter plot stuff and we do a lot of interpreting graph stuff, we deal with primarily single quadrant graphs, okay, meaning quadrant 1, where everything's positive. Okay, now we're moving into another type of graph where we're going to start using our whole Cartesian plane, our whole coordinate grid, where we're using quadrant 1, 2, 3, and 4. So now you're going to have some negative numbers and stuff like that. So This is the most important stuff that you need to put in your function foldable, your function book about linear function. There's one other thing I want you to add with linear function, and that is the picture, some examples of a linear function. So, if we have a Cartesian plane right here, this is our x-axis, this is our y-axis, functions may look like this. And again, I'm not putting numbers on here, but a parent function looks very similar to this. And we always want to put arrows at the end indicating that it goes on forever. You could also have a function that looks like this. Horizontal lines are functions. Unlike vertical lines, which is the opposite, horizontal lines are functions. Okay. If you think about the correlation, we talked about correlation last week. If you think about correlation, this one right here is going in that upward positive direction. So we don't say that this has a positive correlation because this isn't a scatter plot. But what we can say is that that graph right there has a positive slope. And we'll talk more about slope later. So if that has a positive slope, what do you think a graph looks like that has a negative slope? That's right. It's going to go in that direction there. So a negative slope graph goes downward. And just out of curiosity, what do you think the slope of a horizontal line is? Okay, remember we talked about positive correlation was the dots were going in the upward direction, so that's kind of how we came up with this positive slope because this line was going in the upward direction. We talked about negative correlation, the dots are going in the downward direction, and so that's how we kind of came up with this negative slope because the line's going in a downward direction. And again, all this is based on left to right, moving left to right. What's the other correlation that we know or we should know? That's right, no correlation. So the slope of a horizontal line is 0. Okay? And again, we'll talk more about that later. I just wanted to kind of give you a heads up. All right, the next graph I want to talk about, or the next function I want to talk about, is a quadratic function. Quadratic function. Okay? Important things to remember about a quadratic function. Unlike, and all these graphs are going to be different when you graph this, but these graphs create a parabola. And you spell parabola like parabola. Okay, a parabola is a U-shaped graph. Okay, in order to get, and this is a little more advanced than probably the other classes are going to go into this, but I want to talk about it anyways. In order to, because you're going to need to know this for later, sorry. In order to get a quadratic function, a variable must be squared and no higher. Okay, so when we talk about functions, they all have an equation Okay, a function is another word for an equation as well. And so when we talk about a function, then when we talk about the linear parent function, earlier we said the linear parent function was y equals x. If we go back a frame or two, we see that y equals x, and this is our linear parent function right here. And notice how there is no squared variable right here. Okay, well, when you have a linear function, you're not going to have any exponents at all in your equation. Okay, however, when you have a quadratic function, in order to get that U-shaped graph, in order to get that quadratic function, you must have a squared variable. So, with that being said, our parent function, so our parent quadratic function is y equals x squared now. That square term, okay, that square term is an indicator to you that you have a quadratic function. And it not just in y equals x squared, but you could also have y equals x squared plus 3, y equals x squared plus 2x plus 3. You can have any kind of variation, but if your highest term is x squared, or a square value, then you have a quadratic function. If you have a cubed value, now you're talking about something completely different. So if the highest exponent in your equation is a square, you now have a quadratic function. And again, parent quadratic function never changes. This is the same, so you need to memorize that that's the parent quadratic function. And this particular parent quadratic function also goes to the origin. Quadratic functions and parabolas, they don't have slopes like we talked about in linear functions, but we are going to break down a quadratic function and quadratic graphs and stuff like that much later into very great detail. So don't feel like you're getting shortchanged by that, because I promise you will see that later on. Okay? Okay. So let's take a look now, and that's what goes in your quadratic, your function book under the quadratic section. Now I want to add one more thing, and that's the again, examples of the graph. So let's go ahead and look at some examples of parabolas so you can kind of see that. So again, here's our Cartesian plane with no numbers, just generic. Our parent function may look something like this. Well, it's got to hit the origin. Okay, so assume that this point here is actually through the origin. So our parent function may look like that. Parent quadratic function, excuse me. And again, it's tough to have a perfect drawing without the points, but I just wanted to kind of give you an example what to look for. I'm having a hard time with that this right side here. Let me just fix it. Here we go. So our parent quadratic function looks something like this. Okay, right here it's going upward, so it's positive. It's a positive quadratic. And again, we don't really, oftentimes we don't really indicate whether they're positive or negative, but just understand that when it goes upward, it's positive. Again, when we break down quadratics much more, you'll understand more about what that really means. Okay? You could also have a quadratic function that looks like this. It doesn't have to go through the origin. Okay? And in this case, this is going up, this one's going down. If this one's going down, what do you think this one is? It's negative. Okay. And it's not a correlation, so please understand that when I say it's positive or negative, just kind of get that settled into your brain for now. We'll talk more about what the positive and negative mean, but it's not a correlation. Only correlation goes with scatter plots. Okay. So basically a parabola is a U-shaped graph or an upside down U-shaped graph. Okay, one thing I do want to show you is this right here. This is not a quadratic function right here. A graph that goes like this is not a quadratic function, as well as a graph that goes like this. This also is not a quadratic function. And again, we'll talk more about that later in this video. Okay, so that's the quadratic function. Okay, the next two are even more brief because the next two we don't deal with a whole lot, but it is important for you to know. So the next one is absolute value function. It has very similar characteristics to the quadratic. Now again, when I say similar, it's not exactly the same. Similar to the quadratic graphs. I'm not talking about the equation itself. So similar to quadratic graphs, instead of a U-shaped graph, they are V-shaped graphs. Okay. And again, I would just want to abbreviate this. I don't want to go into too much detail on the absolute value graph. But the absolute value, the parent function for the absolute value, so parent absolute value function is y equals the absolute value of x. Just out of curiosity, do you think that it goes to the origin? Absolutely. It goes to the origin as well. And not all of them, not all absolute value functions go to the origin, but the parent functions do. Okay, so that's your absolute value basics. Let's go ahead and look at some examples of this. Again, our Cartesian plane. Now when we look at an absolute value function, we are looking at the parent function looking something like this. Okay, again, not the greatest drawing here, but you get the picture here. And again, it should go to the origin. Okay, so that's the absolute value here. Here's another example of the absolute value graph. It could go like this. And we're not going to even talk about positive and negative in this one because there's a lot more to it than just positive and negative. I just want to kind of give you a picture of what the graphs look like. Again, like the quadratic graph, this right here is probably not possible to make, but is not, just wanted to let you know, is not an absolute value function, nor is this graph here. And again, you'll understand why that is in just a minute. Okay, moving on to the next one. Our last function that we're going to talk about is the exponential function. Okay, the exponential function. This one's a little more complicated than the others, but still not that difficult. And again, we're just going to talk briefly about the exponential function, very similar to the way we talked about the absolute value. When we get into these units closer to the end of, or into the second semester, then we'll talk in great detail about the absolute value and exponential functions. But right now, all we're concerned about really is just kind of identifying these functions. Okay. Again, this graph is a curved. So this is a curved graph that continues to get close to the x-axis, but never touches the x-axis. So it's a curved graph that continues to get close to the x-axis but never touches the x-axis. Okay, and that's kind of an interesting drawing, which we'll see in here in a minute. And I want you to think about this for just a second, okay? I tell this story all the time about this challenge that you could do with your parents. Go home and tell your parents that you could go home and tell your parents that you can feed the entire world with the peanut butter sandwich. Okay? Now, again, I'm not talking about they're going to be full and everything like that, but what happens is that if you go home and cut a sandwich in half, okay, yes, I could eat both halves and the sandwich would be gone. But technically and theoretically, I could cut those sandwiches in half again, and I can cut them in half again, and I could cut them in half again, and I can cut them in half again, and I'm never, ever, ever going to get to zero. That peanut butter sandwich will never go away. But again, you're talking about obviously very, very tiny, 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 tiny halves. But if I halve something forever, it will never get to zero. I can never get to zero. And that's why the exponential graph never touches the x-axis, so it doesn't have an x-intercept. Okay. The other thing that you need to know about the exponential graph is that it doesn't necessarily have a parent function, it's got a general form. So the general form for an exponential graph, not but form, is y equals a to the x power. So that's your general form. Notice here the big huge differences here. Now you have x value, because when you graph these, and you'll learn more about this as we move on, you have your x and y axis, your independent and dependent coordinates. Your x coordinate now is an exponent. In every other form, your x coordinate is not an exponent, it's just a base number, but now all of a sudden it turns into an exponent. Okay, let's go ahead and take a look at some of the pictures of exponential graph. Again, our Cartesian plane, an exponential graph could look something like this right here. I'm going to start up here, and it's going to curve and go closer to x, closer to x, closer to x. But as it continues to go down, it will never cross the x-axis. And it's going to be very difficult for you to draw that, but you just need to make sure you understand that concept, because it's hard to always see that. Okay? Another exponential function could look like this. Could go this direction. And again, it will never cross the x-axis. Alright, so that is your exponential graph. And again, I don't want to go into much more detail other than that. We'll talk more about that much later. Okay? I want to talk about a couple more quick bits of notes that you might want to put in this function book somewhere, but it's basically a vocabulary deal. Okay, the first thing is function. So I've just told you about a linear function, a quadratic function, absolute value function, exponential function. So you might be sitting there saying to yourself, well, what is this word function all about? Okay, so a function, and this is one of your vocabulary words that you will be responsible for on your vocabulary quiz, or vocabulary test, excuse me. So a function, and I'm not going to give you every one all the time, but this is one that I want you to have and make sure you write in your function book. A function is a relation. And a relation means it has an x and y. Okay? A function is a relation in which none of the first coordinates repeat. Okay, and that's kind of a watered down definition, meaning that it's not mathematical, using a lot of math terms. So what I want to do is I want to give you a more mathematical definition. Okay, it's a relation where the x values, or you could call them independent values, do not have more than one associated y value, and a y value is dependent. And again, knowing this definition here is more of a kind of a higher level understanding of that definition of function. And again, understanding the independent for x and dependent for y will actually get you ahead a little bit in the class, but we're going to talk more about that again. And again, another way people say it, and again, not the definition, but a kind of a shortcut is all of the x values in a function are different. So that's another way to put it. Okay? So that's a function. All right, so your last page of your function booklet, and I know this has been a long video, but I told you they get longer. Again, if you make sure you take care of what you need to in class, all you have to do is watch a video, which is much better than doing a whole bunch of homework. Okay? Finally, the last thing I want to talk about, the last thing in your book, is the vertical line test. Okay? So, vertical line test. Okay? Basically, a vertical line test is this. If I can draw, or I guess I should say if you can draw a vertical line through any point on a function, comma, then the function, then okay, so if you can draw a vertical line through any point on this should be graph, I apologize if you already wrote that, on a graph, then the graph represents a function. Represents, I know that word doesn't look very clear, represents a function. Okay, so vertical line test. If you can draw a vertical line through any point on a graph, hang on, let me correct that. If you can draw a vertical, if you can draw a vertical line through any point on a graph, and it only hits the graph one time, okay? So that's what it should say. So again, I apologize. I left out some stuff there. My brain was working faster than my pen was writing, okay? So it says if you could draw a vertical line through any point on a graph and the vertical line only hits the graph once, then you have a function. All right, sorry for that inconvenience, that trouble. So if you can draw a vertical line through any point on a graph and the vertical line only hits the graph once, then you have a function. Okay? Big definition. Let me give you a visual representation of what that means. So here we go. Actually, we're going to use what we have. So let's go back to the graphs that we looked at earlier. So on the linear graphs, that's quadratic. One more. On the linear graphs, if I draw a vertical line through this graph and it hits once, it's a function. So let's take a look. So on the black function there, the horizontal line, it only hits that graph one time. On the blue function, the negative function, it only hits that graph one time. On the red function, it only hits that graph one time. Okay? And no matter where I draw this pink line, it's only going to hit that graph one time. So that means I have a function. Earlier I said a vertical line was not a function. So let's determine why. Why is a vertical line not a function? Well, let's look at it. If this is a new function, this vertical line here, or a new graph, excuse me, not a function, and I perform the vertical line test on this graph, is it only going to hit this graph one time? Okay? Now, when I perform the vertical line test on this graph, it hits every point on that line. So it hits more than one point. So this is not a function, because it fails the vertical line test. Instead of hitting one point, it hits every point. It fails the VLT, which is my abbreviation for the vertical line test. A lot of people get that messed up. Just memorize the fact that a vertical line is not a function. If you memorize that fact and that it fails the vertical line test, then you'll be good to go, because a lot of people screw that up. All right, so let's look at quadratics. Okay, we said that the black line was not a function. Whoops. And let's prove why it's not a function. The black line is not a function because it hits the line 1, 2 times. Remember, we can only hit it once for it to be a function. What about the blue line? The blue line is a function because it only hits that graph one time. And no matter where I put that red line, that pink line, it's only going to hit the graph one time. You got to be able to put it anywhere. Same thing with the red one. Look at the red one. The red one is a function as well because it only hits that graph one time. Okay, that pink line only intersects with that graph one time. And no matter where I put that pink line, it will only intersect one time as long as I draw straight lines. But now look at that yellow graph. It's not a function, again, because it hits more than one time. You can see right here, 1, 2. Here, 1, 2. Now in this particular spot, it does only hit one time, but because it hits 2 times in the other spots, it's not a function. Okay. So that is the vertical line test in a nutshell. Okay, so hopefully you understand the vertical line test from that. Again, I apologize for the video being so long, but that is just part of the nature of the beast. It's better than me standing up there talking for 46 minutes in class. Now you can watch the video, come in tomorrow, and do your work. This is very, very, very important information, so make sure you have this all down in your notebook. You guys have a great day, and I will see you tomorrow.